Jae. I'm a postdoc from the CMOS group. I'll talk about the semiconductor fabrication processes today. I hope you guys can understand my poor English during the talk. So to start with, I go through circuit elements, fundamental circuit elements with materials based on metal and dielectric and semiconductor. They are divided into three based on in terms of electrical conductivity. If the conductivity is larger than generally like 100 siemens per centimeter, it will be metal. So the metal only circuit element might be resistor and inductor. And if we integrate this metal and then dielectric together, dielectric has a conductivity which is lower than approximately 10 to the minus 8 siemens per centimeter. So if we integrate those two, we can have a capacitor structure that where we can store some charge. And for the semiconductor, it has a conductivity in between 10 to the minus 8 to 100 siemens per centimeter. And we can make a famous PN diode using the semiconductor material if we dope N-type or P-type, N-type and P-type atoms into the semiconductor. And finally, if we merge these three materials all together, we'll get a metal oxide semiconductor field effect transistor, which is the most widely utilized transistor in the industry, and it's also a basis for the integrated circuits. So I talk on the fabrication process guideline using this based on this MOSFET device, and also if we tie the source and the drain junction, like here, we can make a semiconductor capacitor as well. So, yeah, this is a brief summary of the circuit elements. So, as I told you before, this MOSFET device is a basis for not only the analog circuit, but also the digital circuits as well. So, this transistor size is kind of a reference number for the industry. This is a photo taken from the Intel in 2014 for the 14 nanometer node of the transistor. So before getting into details, I'll point out the most critical parts in the fabrication process. So the transistors are in the beginning made on the silicon wafer, and in each step, different materials are deposited and they are etched after this photolithography process, which is similar to printing press. I'll talk about detail after like 40 slides after. And it is very easy. It is easiest way to understand how the structures are made by looking at from the both top and the cross-sectional view. The next slides will be explained with top and cross sections with simplified manufacturing process. So this is a finalized inverter structure. You can see here. So typically we use P-type substrate silicon wafer for the N-type MOSFET. But this is a CMOS inverter, so we have a complementary P MOSFET next to the NMOS, which needs a N-well to control the channel. So to control the P-type channel, we need to have an N-well here. And there are several alternatives like silicon on insulator wafer or twin top structures. For the inverter to actually operate, we need to know how the electrodes are tied in the silicon surfaces. It is way easier to understand the inverter operational scheme by looking at the inverter circuit. So if you recall it, the inverter looks like the two MOSFETs putting together, and there is an input here, and there is a supply voltage, and there is a ground, and there is an output. So from the PMOS here, it's connected to the supply voltage as here. And then for the NMOS, it's connected to the ground. And here, this one is input. This is for the output. So it's how the inverter structure looks like. And to have a contact between the metal and the semiconductor surface, we need a semiconductor surface to be highly doped as high as possible. Because if it is like very low resistive, very high resistive, there is going to be a shocky resistivity in between the two, which induces a lot of resistivity, which is very bad for the transistor operation. So we need this substrate and the VDD tab to be highly doped, like here. This inverter circuit looks very simple just by putting two transistors together, but actually there are many more steps when we actually want to make it, like here. So we need some layout using mask sets like this. This mask will be 6 masks, like here, from N-well to metal. This is a minimum number of mask sets we can have for making inverter. Because in the state-of-the-art industry, we need the device to be very small, like few nanometers. So there should be a finer or like extremely smaller patterns included in it. So we need a finer technology inside the inverter making process. So which means we need more masks, like 10 or 20 or even up to like 50 mask sets we need just for the inverter. So let me begin with the very beginning. So we start with the silicon blank wafer, like here. And we build the inverter from the bottom to the top side, so we call it bottom-up process. First, we make an N-well junction. To make the N-well junction within the pre-designed location, we need a SiO2, which will block the atoms to go through the silicon area. So we grow the silicon dioxide on top of this silicon wafer with a temperature of 900 to 1200 degrees Celsius with water or oxygen ambient furnace. And then we spin coat the so-called photoresist. Photoresist is a light-sensitive organic polymer. If we expose the light on UV light onto this photoresist, it gets softened so that we can remove it. So using the pre-designed mask like here, we expose a certain area like this and then shots the light onto it, and the photoresist will be exposed to the light and it will get softened. And then we apply a liquid that is called developer, and then we remove the exposed photoresist area out. This is a photo taken in the Marcos clean room. It's one kind of photolithography tool called MA6, which stands for mask aligner for 6-inch wafer. There's also a mask lease photolithography tool called Heidelberg. We use exposure, some kind of wizard graphic unit to work as a mask here. So this does not need mask when we actually fabricate something. And then we etch out the oxide where the photoresist is exposed and removed using this hydrofluoric acid, or HF. This HF is really, really strong and powerful, so it can melt down your skin or bones. This HF only affects the exposed photoresist removed area, because the other locations, they are all covered with photoresist, which blocks the HF. there's also another source that can etch the silicon dioxide, which is a plasma. So here is a photo of a plasma glowing. It's also equipment in the Marcos building. This is another photo from the from another dry etch equipment. The dry etch is what it is we don't use a liquid for that, so it's called dry etch. So and when we use liquid like HF, it's called wet etch. So this is a microscopic photo taken for after the oxide has been patterned out. Since this photoresist has its job done, we strip off the remaining photoresist so that we can only have silicon dioxide below it. Using the solution called Piranha, which is a mixture of sulfuric acid and hydrogen peroxide. And then we make an anvil finally, using either diffusion or ion implantation process. This diffusion equipment is generally more cheaper than ion implantation equipment. So, but the controllability is way worse compared to ion implantation. Since most of the research institutes or like universities deal with very large scale, like micrometer scale, so they tend to have diffusion tools rather than ion implantation equipment. But the industry should have ion implantation tool to make it more finer. For the diffusion process, we place the wafer in the furnace with arsenic gas or phosphorus gas for the N-type well. For the P-type, we need boron. If we look at the periodic table, there is a group 3, group 4, and 5, there is boron, silicon, phosphorus, and arsenic. So when these side elements want to be bonded with silicon, the group 3 elements tend to accept electrons because they have 3 electrons in the outer ring. For the group 5 elements, it tends to release their electrons. So the group 3 elements are called acceptor, while these group 5 elements are called donors. So in this case, we are using an N well here, so we are using either phosphorus or arsenic gas. And we heat it until these arsenic atoms diffuse into the exposed silicon like here. On the other hand, for the ion implantation, we blast the wafer with beams of arsenic ions like this. And then these ions are blocked by the remaining silicon dioxide so that we can have an annular junction in the pre-designed area. This is a photo taken from the Marcos clean room for the diffusion furnace. Same thing here. And then we strip off the remaining oxide using, again, the HF. And then we are back to the bare wafer again. And the subsequent steps will be pretty much similar with the previous steps I went through. Finally, we make our gate here. Actually, before making our gate oxide, we need to clean the wafer as clean as possible because this gate oxide area is the most significant part of the transistor, using a process called RCA cleaning. So after cleaning it, we deposit or oxidize the silicon surface up to the thin layer of gate oxide of approximately 2 nanometer. And then we chemically vapor deposit the silicon layer on top of it so that we can make a gate. We place the wafer in the furnace with silane gas, which makes silicon gate. And then if we heat it, it forms many small crystals and then forms a polycrystalline silicon, which is called polysilicon. Because the gate is supposed to have a high conductivity as metal, we need to heavily dope the gate as possible so that it can be a good conductor. And then we have another set of gates here, mask here, to make a gate like this. And it is time to make a source and drain junction. To make it, we need another oxide on top of the silicon wafer to block the unwanted area to be doped. So we deposited oxide here again. And then we use the source drain for N-type junction mask here. And you can notice that the source and drains should be located next to the gate here and there. But if you look at the mask here, the gate side is also open. This is because gate can block the ion coming from the implantation tool, and it can work as a mask itself. So it's called self-align process, because it can self-align without mask. So what happens if we expose this and if we make it blocked for the gate area, then it will be there could be some misalignment issue, so that some of the area cannot be doped in the source drain junction. So we'll have a high channel resistivity. We don't want that. So we normally use this self-aligned process. But for the metal, we cannot use this self-aligned process because after the self-alignment process, we need to heat it up to make the source drain junction conductive. But this heat would make this metal to be melted down. So only the polysilicon gate is available for the self-aligned process. So again, we diffuse or ion implant the source drain junction like here. And then heat it up so that you can activate the ions with silicons, and then for the second to drive in the junction so that we can make some junction depths what we want it. And then we strip off the remaining oxide again, and so that we can have this kind of structure here. And then with the same process, we also make a P junctions like this. So finally, we made the transistor up to this point. So since these are transistors, we call the process steps up to now as a front end of line. And after this transistor process, we call it back end of the line. For the beginning of the back end of line, we need to make a hose for the electrode connection. For the electrodes to be connected to the silicon surface, we need first to cover the chip with thick field oxide to isolate in between the electrodes. So we deposit the thick field oxide, and then we make a hole like here, and then we deposit the metal using physical vapor deposition, and sputter is one kind of that. And then we pattern the metal out, and then make an inverter. So this is a finalized inverter photo from the microscope. You can see that there is an N well in the bottom, which means there is a PMOS in the bottom and then NMOS in the top.
Question.
Yep.
Do you need to connect the contacts to VDD and ground, like the heavily doped P plus and N plus?
So your question is, why do we need to heavily dope this P plus and N plus?
Actually, my question is, do we need to connect this area to VDD or ground?
Yeah, that's exactly from the circuit I drew.
Oh, okay.
Yeah, so it's, if you recall that stuff,
yeah.
you can.
Okay. Can you also explain why you said there needs to be a P plus and N plus heavily doped area?
Yeah. Actually, so if a low resistive semiconductor is connected with the metal, it'll make a shocky junction, which means it needs some voltage to turn it on, but we want it to be like ohmic status, right? Like metal, just a metal. But if it is low doped, then it'll induce a really large resistivity between the electrode and the silicon. So we don't want it. So we make it P plus or N plus. Yeah.
Oh, I mean, is that extra P plus next to N plus for ground? Like the left bar, you have a P plus next to N plus.
Yeah, this is for the source and drain junction.
And how about P plus net?
This one is for the body contact.
Yeah.
So this is CMOS here at the bottom. So this is ground.
Mhm.
So you want this to be connected. This drain side should be the source side should be connected to the ground.
Mhm.
So this one will be here and there
Uh-huh.
together,
Okay.
and then this one will be
Good.
left.
Yeah.
Can you explain why connected to that P plus area can give you a ground? Like, why not just connect it with the silicon? Why does it?
So it's a P-silicon, right?
Yeah.
So basically, to make an ohmic contact to your silicon, you need to heavily dope it so that it doesn't form a Schottky barrier like you mentioned. So because it's a P-silicon, that's why you need heavily P plus doping at that point so that you can make a ohmic contact with it.
I see, but the purpose is still connecting the transistor with the whole wafer.
No, this is to apply a body bias to your entire wafer. It's not, your transistor is connected. So basically you can adjust your threshold voltage. Like body bias can be used for different reasons, but basically you are applying a bias to your substrate is what you're doing. So you can adjust your threshold voltage or other things you can do.
I think now I understand what your question is. So why there is P plus and N
Yeah.
plus together, why just not N plus altogether?
Yeah.
Okay. So this is body substrate bias, which is a reference value for tuning the VT, threshold voltage. So we need this P plus to be there to properly connect to the body. Yeah, it's working as a body bias. So yeah, I'll talk about more detail after this class.
Sure.
Okay, let me go on to the next slide.
Yeah.
So up to this point, we've gone through this transistor fabrication process, inverter fabrication process. So there is some missing point we didn't go through, which is a design part. So as I mentioned earlier, we need mask sets, which is a layout for chip making. So the minimum dimension of the mask will determine how the transistor size will become. If the transistor size is as small as possible, is smaller, then the speed will be faster and it will be more cost effective and more power efficient. There is a reference value to make a design, which is a feature size F. This is a distance between the source and the drain, which is gate length. This feature size improves 30% every 2 to 3 years or so. This speculation has been found by a famous man called Moore. So it's called Moore's law. By improving 30%, it means the size radius of the chip will become 0.7 times smaller. So if we times those two together, it will be like 0.49, which is about half. So we also say the Moore's law, we also state the Moore's law as the number of chips become twice every 2 to 3 years. And then we can also normalize the feature size when describing these design rules. by dividing the feature size to 2, and we get lambda. So we use this lambda to define many kinds of mask sets we need to have, like here. So these are some conservative rules to make a mask. Could be a little different from company to company, but yeah, it's pretty reliable design rules that have been used for decades.